All right, so last section this week we're going to look at is 7.4, which is on identities. 7.5 is on identities, and then I think there's even more in 7.6 maybe, I'm not sure. But the next few sections are all going to be on identities. So remember, an identity is an equation that's true all of the time. So when I give you a trig identity, it's not a formula that only works some of the time. It's a formula that works all of the time, no matter what numbers you were to plug into it. So we're not really concerned about plugging numbers in. That's not really the goal. So an example of an algebraic identity would be something like this. If you were to solve that problem, you'd end up with 3x plus 6 on the left, and you'd end up with 3x plus 6 on the right. Well, if you subtract 3x from both sides, you end up with 6 equals 6. That's an identity. That means that no matter what number you plug in for x, you're always going to get exactly the same thing on the left as you do on the right. And the goal is to find something that is exactly the same thing, but simpler. Right? So maybe what's on the left here would be considered simpler because it took the like terms and combined them, and it factored out the GCF. Right? Where the right-hand side didn't do that. So there's some identities that we should be familiar with, and I'm going to put those up. All right, so these are identities that we've worked with before, especially when we have to type something in on a calculator. We don't have a way to type in cosecant, secant, or cotangent, so we have to type it in as 1 over. 1 over the sine is the cosecant, 1 over the cosine is the secant, and 1 over the tangent is the cotangent. That's the most common way to use the reciprocal identities. But you can also do it kind of the other way. If you flip sine, you get cosecant. Well, if you flip cosecant, you get sine. Same thing here. If you flip the cosine, you get the secant. Well, then if you flip the secant, you get the cosine back. So these are 6 different reciprocal identities, but there are really only 3. These 2 are repeats of each other. So are these 2, and so are these 2. If you're saying what's in those boxes is different, that's like saying this is 2 different formulas. And that's not 2 different formulas. That's just 2 different ways of writing the same formula. That's what's in these boxes. 2 different ways of writing the same exact thing. Okay, and those are called reciprocal identities. Okay, another type of identity that we can use to simplify problems are the tangent and cotangent identities, which are called the quotient identities. And the quotient identities, there's 2 of them. It says that sine divided by cosine gives you tangent, and cosine divided by sine gives you cotangent. Now, I'm not going to write out this for every single formula, but does anybody have a guess what this would be? Sine squared x over cosine squared x. And if you're not sure, think of it like this. Sine times sine over cosine times cosine. So you have a sine over a cosine times another sine over a cosine. What do you think this would be? Nick?
Tan 1 tangent.
So sine over cosine is equal to tangent.
Yeah.
But how about sine squared over cosine squared? Yep.
2 tangent?
Well, what's sine over cosine? What did we just say?
Tangent.
And what's sine over cosine?
Tangent. Oh, so it'd be tangent squared.
So that would be tangent squared. So a lot of these identities do work with higher powers. Same thing here. If you flip the sine, you get the cosecant. Well, what if you flip the sine squared? what do you think you would get? Yep.
Secant squared.
You would get the what? So if you flip sine, you get cosecant.
Yeah, that's right.
So if you flip sine squared,
You get cosecant.
you would get cosecant squared. Okay, if you flip sine cubed, you would get cosecant cubed. So all of the identities that I just gave you for the reciprocal and quotient, they work with higher powers. Generally, we don't go any higher than a power of 2. So you really don't have to worry about going really high with them. And the last group of identities are the Pythagorean ones, and they don't work with higher powers. They only work exactly the way you see them. And there's 3 of them. There's sine squared plus cosine squared equals 1. That's the first one. 1 plus tangent squared equals secant squared. That's the second one. And the third one is 1 plus cotangent squared equals cosecant squared. Now, these identities don't work with higher powers, but what you can do is something like this. Take this one. If I wrote this, what do you think would go on the left-hand side? Yep, yeah.
Sine squared x.
Sine squared x. This is just called a rearrangement. That's all we did. Is we rearranged a Pythagorean identity and put something on the other side. You can do that with all of these. So there's different ways you can put something on the other side. So the key is when we have problems that have sine squareds and cosine squareds, we're probably going to want to think of using this somehow, but it might be rearranged. We might move something to the other side. And you can do that with the other ones as well. All right, so those are the 3 main groups of identities that we're going to study in this section. Reciprocal, quotient, Pythagorean. Questions on those? And what this all really kind of boils down to is doing substitution. You're going to be substituting in something that's hopefully simpler than what you started with. Like if you have a sine over a cosine, you could substitute in a tangent for that. It's simpler. It's one trig function, and it's not a fraction. Not every problem is going to have every one of these identities in them. These are just kind of the ones you can pull from to solve the problem. All right, so let's try some examples. So in calculus, the idea is you may have a problem that's asking you to do, like, say, an integral or a derivative. Those are 2 things you'll learn in calculus. Doing an integral or a derivative with a fraction can be complicated. If you can turn this into something that's not a fraction and then do an integral or derivative, it's going to be a lot easier. So if we can just get rid of the fraction using trig, life becomes easier when we have to do the calculus part. So one trick that we can use to simplify a problem that has trig in it is to change everything in the problem to sines and cosines. There's always a way in trig to take any expression, no matter what trig functions it has, and turn it all into sines and cosines. And a lot of times when you do that, things will cancel out. You want to keep in mind all your basic properties from algebra. This is the kind of problem where you'd use distributive property. Let's say you had a trig function on the outside. You could still do distributive property, right? So even rules that we learned back in algebra are still going to apply to everything we're doing today. Like x times x equals x squared. Well, sine x times sine x is sine squared. It's the same exact thing as doing x times x. If you had x plus x, that's 2x. Sine plus sine, that's 2 sine. Okay, all those kind of rules still apply when you use a function instead of just using a variable. And we're going to see lots of trig functions. All right, so let's look at this one. Cotangent divided by cosecant. It doesn't really matter what the argument is. The point is this argument will always be a variable. X, Y, theta, something. Let's try using the trick that I just showed you. Change everything to sines and cosines. How can we rewrite cotangent in terms of just sines and cosines? Caleb?
Cosine over sine.
Yep. It's cosine over sine. And you might think, well, geez, now this is starting to look even worse. It usually does look a little bit worse before it gets better. And now cosecant. How can we write that? Just using sines and cosines. Yep, that's
1 over sine.
That's 1 over sine. Now, how do you take and divide a fraction by a fraction? Don't worry what the fractions are, just in general. How do you divide two fractions? Yep.
Multiply by the reciprocal.
Multiply what by the reciprocal? The top. So keep the top the same and multiply by the reciprocal of the bottom. So that's going to be sine over 1. And when you multiply those two fractions together, what happens? Yeah?
Sine cancels each other out.
The signs cancel each other out. Anytime you have two fractions and you're multiplying, you can cancel if the same thing is in the top and the bottom. Right? You cancel the 8s. You cannot do that if it's addition. Addition or subtraction, you can't cancel if the same thing is in the top and the bottom. You can only cancel when you have multiplication. If you have addition or subtraction, now we got to get into common denominators. That's different. Okay? But in this case, that's perfectly fine. And what are you left with here as the final answer? Maybe?
Cosine.
Cosine. So we started with a problem that had two trig functions in a fraction, and we ended up with something that's equivalent, and that's much easier to work with. Single trig function, no fraction. A lot easier now if we have to do calculus with this. Yep.
So anytime cotangents over cosecant, we get cosine.
Yeah, yep. Not an identity that I would memorize off the top of my head. These are ones that I have memorized. Well, the other ones I showed you. Off the top of my head. These I am. This, I don't know, but I could figure it out in about 10 seconds. Yep. And there's, again, thousands of these kinds of things. But that's one that would be considered simple. That's a simple one. Yep.
What happened to the 1 over sine?
Since we're dividing by a fraction, we flipped it and we multiplied.
Okay, thank you.
Yep. So all the rules that you know with numbers, you can do the same kind of thing with functions. Any other questions on that? All right. Let's try this one. Cosecant times tangent. How can I rewrite cosecant? So
1 over sine.
1 over sine times, how can I rewrite tangent? Yep, Tim?
Sine of x divided by cosine of x.
Yeah, let's just stick with the argument letter that they used in this case, which is theta.
Oh yeah, sorry.
Yep, that's fine. So sine over cosine. And what's going to happen there? Yep,
Cancels.
what?
Sine.
Sines cancel. So what am I left with right now? 1 over cosine. And then there's always the question of, well, should I stop there or should I change that? I would argue if you can write something not as a fraction, then that's simpler than having a fraction. So what is 1 over the cosine? We would use this on the graphing calculator all the time. Yep?
Secant.
That's your secant. So if you want to take the cosecant of any angle times the tangent of that same angle, it's exactly the same as just doing the secant. Okay, question on that? All right. So when we're asked to verify, that's a little bit different, but it's actually easier than simplify. Simplify is kind of open-ended. They give you a problem, and you just keep going till you think you're done. You never really know when you're done. I mean, sometimes it's clear, like in this case, I would say it's pretty clear. I mean, what else are you going to do with secant? It's a single trig function. I mean, you can't do anything with it. But in a verified problem, which don't write it yet, but in a verified problem, they give you something on the left, they give you something on the right. The goal is to turn one side into the other side. So it's like you know what to start with, you know what to finish with. Get the steps in the middle to get me from the start to the finish. So verify is a little bit nicer because you know what the final answer is. You just have to get there. So verify means prove that what's on the left and what's on the right are equal to each other. This is the approach that we're going to use. We're always going to start with the side that looks more complicated and simplify it. It's a lot easier to take something that has, or take something that's more complicated and make it simpler. Don't try to take the simple side and make it more complicated. You always want to take something that's complicated and simplify it. And hope you end up with what's on the other side. Now, the other approach is to work with both sides at the same time. We're not going to do that. We're going to stick with just working with one side at a time. But technically, if you had two sides that were different, you could do a little work on the left, do a little work on the right, do some more on the left, do some more on the right, until eventually you get them to match. But I would say this approach, when you're starting out, is probably the way to go. All right, so there's really three main tricks I'm going to show you. Tricks are like things to try in the problem. One trick is to change everything to sines and cosines. Another trick is if you have two fractions with different denominators, find a common denominator. And that will usually make something nice happen. Right, so I'm just kind of introducing these tricks as we go. I'm not saying every problem is going to use every single trick I give you. But when we do the next problem, something like this might come up now. Finding a common denominator. That did not come up in the first two we did. Didn't need that. All right, so let's try one more simplified. Again, that's kind of the open-ended question where you just kind of go at the problem and keep going until you think you're done. And then we'll do a verify. All right, so let's simplify this. Sine times, in parentheses, cotangent plus tangent. Does anybody see a property that you learn in algebra that might apply to this problem? Yeah?
Distributed.
Yep, this is a distributive property. If you were thinking, well, should I change it to sines and cosines? Because you taught us that too. Yeah, you should. It doesn't really matter what you do first. You're going to have to distribute eventually, and you're going to have to change to sines and cosines. So you need to do both. I'm going to start with distributive. So I'm going to have sine times cotangent plus sine times tangent. And again, now it looks more complicated than what we started with. Yep, that's usually going to happen. All right, so we did the distributive property. Now, what could I do with everything that's there? Yep,
Make it sines and cosines.
let's make it sines and cosines, even if we're not sure how that's going to help us. Just try it, maybe something will cancel out. Since we're going to end up with fractions, I'm going to make everything a fraction right now. Okay. What is cotangent? Michael?
1 over tangent.
It is 1 over tangent, but that wouldn't be changing it to sines and cosines. Not saying that's not going to help us sometimes, it might, but not in this one. Yep,
Cosine over sine.
let's make it cosine over sine. Plus, be very careful with that plus. Remember, a plus, think of it as like a brick wall in the problem. You can't cancel anything on one side of a plus sign with something on the other side. Multiplication, yes. Plus, no. So we got sine over 1 plus, what's tangent? Yep, that's
Sine over cosine.
sine over cosine. All right. So if you're thinking, well, wait, cosine in the top, cosine in the bottom, no, don't, can't do that because that's across a plus sign. Is there anything that's on the same side of the plus sign that we can cancel? Yep, so
Sine
Yep.
over sine.
we can cancel these signs, that's fine. Let's leave this as cosine over 1 plus anything we can cancel on this other one. Yep.
No, but instead of making it sine and cosine, could you first make tangent into cotangent by doing it like switching it 1 over tangent? And then you end up with sine on the top from going through with that eventually. But you end up with sine on the bottom.
So yeah, there's always other ways to do identities. I'm not sure. I'd have to look at that approach and see how that one would work compared to this one. Some ways are faster than others. I'm going to continue with it this way, but you could definitely try that and see what happens. All right, so we gotta do something with this now. Yep.
Well, would you just multiply them for sine squared and then over cosine?
Yep. So sine squared over cosine. So now you've changed everything to sines and cosines. So we've used that trick. What's the other trick that I just taught you? And it's going to come up right now. Yep.
Common denominator.
Common denominator. So remember, the easiest way to find a common denominator, if you had something like this, you could just take the two denominators you have and multiply them together. It won't always be the smallest denominator, but it works. So in this case, I would use 35. Each fraction gets multiplied by the other denominator. Okay, it's basic adding fractions. We can do the exact same thing here. What would be my common denominator between these two fractions? Michael?
Cosine.
Cosine, and that's great because one of them already has a denominator of cosine. I don't even need to change this one. So my common denominator is cosine. The right fraction already has it. The left fraction does not. So, what would you have to multiply the top and the bottom by to make it the common denominator? Yep.
Cosine.
Cosine. Now, cosine times 1 is cosine. There's your common denominator. And what's cosine times cosine? Yep.
Cosine squared.
Cosine squared. Okay, we've changed everything to sines and cosines. We've rewritten it with a common denominator. At this point, there's something here that we need to recognize that I wrote down at the beginning. Something there simplifies a lot. Tim?
Sine squared of x plus cosine squared of x is equal to 1.
Great. That numerator, cosine squared plus sine squared, is the first Pythagorean identity that I gave you. Cosine squared plus sine squared equals 1. So that entire numerator turns into a 1. So now I have this. And what do you get when you flip the cosine? Yeah, secant. So look at how complicated of a problem we started with. Distributive property with 3 different trig functions, and the whole thing reduced down to just a simple trig function, secant. That one would be maybe like a medium easy. Not super easy, but maybe a little harder than the last 2. A little bit harder. Okay. Any question on that one? All right, let's try this one. So this is a verify, which means we know what to start with, assuming you can figure out which side looks more complicated. We know what to start with. We know what to finish with. The goal is to turn one side into the other. Which side here is definitely more complicated? Yep.
The right side.
Yeah, the right side. So what we're going to do is work with the right-hand side, and we're going to try to simplify it into the left. Until I get going, I don't usually know exactly what I'm going to do. Okay, I just kind of start thinking about it, different things I can try. If I start one of these problems, and I realize as I go, it's getting worse and worse and worse, and things are just not good, then I stop. I'm like, all right, I need to start over, and I need to try something different, because it's not getting anywhere. So I'm going to write this down. And now we have to figure out what we might want to try. Any suggestions? What I try here? Yep.
Well, you could put tangent into sine over cosine plus
Yeah.
cosine over sine.
I would try changing everything to sines and cosines, especially in the bottom. I'm kind of debating what I want to do with the top. I think I'm just going to leave it as secant for now. I might end up changing it eventually, I don't know. But I kind of want to see what the bottom turns into first before I change the top. So I'm going to keep the top the same. Again, I might end up changing it, I don't know. But let's rewrite this. So tangent is, what did you say, Mabel?
Sine over cosine.
Sine over cosine. And what about cotangent?
Cosine over sine.
Cosine over sine. Okay, that at least pointed me in a direction, because now when I look at the bottom, I think of something I can do. What trick could I try in the bottom now? Yeah? I would now try the common denominator. So at least I have a direction I think I'm going in. If I decide it's not looking great, I'm just going to stop and maybe try something else. Oh, so again, I'm just kind of keeping the top the same. I think I'm going to end up changing it to 1 over cosine. I'm just not sure yet. What is my common denominator in the bottom? Yep.
Cosine times sine.
Yeah, cosine times sine, or sine times cosine, however you want to write it. Cosine times sine. What is the denominator on, or what's the fraction on the right going to be multiplied by to make it the common denominator? Yep. Cosine. This is just like the one I did with numbers earlier. And what's the fraction on the left going to be multiplied by? Yeah. Sine. And anytime I start to see sine squareds and cosine squareds, I like that, because I know it's going to turn into a 1 somehow. But just go one step at a time. So we've got the cosine times sine in the bottom. Sine times sine is sine squared. Plus, what's cosine times cosine? cosine squared. Now, again, this top, I just kind of keep copying it down. I'm still not 100% sure what I want to do with that yet. Secant divided by, what's sine squared plus cosine squared?
1.
1. I probably would have done that in the previous step. I wouldn't have rewritten it another time just to do that one thing. Otherwise, if you rewrite every single step one at a time, you're going to end up copying it a lot. But if you want to see everything done out, then that's fine. Cosine sine. Okay, I do think I'm going to change the top at this point. I'm actually just going to do it right here so I don't have to write it another time. What is secant if we rewrite it? Yeah?
1 over cosine.
1 over cosine. So I guess by changing it now and not changing it earlier, it saved me a little bit of writing. So instead of having to write a number, a fraction bar, 3 letters, and a theta, all I had to do was write 3 letters and a theta up until the point I wanted to change it. So it saved me a little writing. Okay, now I have a fraction divided by a fraction. How do I handle that? Yep.
I'm gonna do 1 cosine times cosine times sine over 1.
Yeah, look at what's going to happen here.
Cross out
Yeah, what's going to cancel?
the cosine and the 1s.
Yep, cosines cancel, the 1s cancel. What are you left with?
Sine theta.
Sine theta. Let's scroll back up because this was a verify, so we knew what we were supposed to get. Let's see if that's what they said. Perfect. That's exactly what they told us to get. So we verified that this does turn into that. Is that the fastest way to do it? I don't know. Probably. But that, that's the path that we kind of chose. Okay. Any questions on that one? Okay, again, I'm probably making a lot of these look easy. If you make one little mistake, like let's say you accidentally forget to put this here, then you start to get totally stuck. Because you're like, well, wait, this kind of looks like an identity, but it's missing the 2. Well, it's missing the 2 because you forgot it. So sometimes a little mistake totally messes you up. But we haven't made any major kind of mistakes yet. All right, so let's see, a third trick. So we've got changing to sines and cosines. We've got finding a common denominator. The third trick is to multiply top and bottom by a conjugate. A conjugate would apply in this type of situation. It's when you have a fraction, and part of your fraction has a binomial in it, 2 terms. The conjugate is when you change the sign that's between them. So this would be an example of multiplying top and bottom by the conjugate. I think we're actually going to do one very similar to that. Yeah, almost the same thing, right? Kind of. So conjugate applies when you have a fraction and you have a term, where you have a numerator or denominator that has 2 terms in it, just like that. Usually one of the terms is a number and the other term is a trig function. And this is a perfect example to do a conjugate with. 2 terms, one is a number, one is a trig function. And remember, when you multiply 2 binomials together, this is a FOIL. You have to FOIL this out. And the conjugate that you use, it could be in the top or it could be in the bottom. In this case, it was in the bottom. You wouldn't do a conjugate of what's in the top because that doesn't have 2 terms. That's just 1 term. So a conjugate wouldn't apply in the top of this problem. Changing to sines and cosines wouldn't apply in this problem either because it already is. So when those 2 tricks don't work, then we try the conjugate. Right, so let's try this one. Now, the last verify problem, I think it was very clear cut which side was more complicated. There's no question the right-hand side was more complex. In this one, they're about the same. I don't really think you could argue one side is that much more complicated than the other. They're almost like mirror images of each other. It's like they both have sines and cosines. They each have a single trig function in part of the fraction, and they each have a binomial in part of the fraction. So they're kind of the same thing. So it's not going to be that satisfying of a problem because when you're done, you're not really ending up with something that much simpler than what you started. But that's what they want us to try. So you guys want to start with the left-hand side or the right-hand side?
Right.
Right?
Left is right. Oh, well,
What's that?
I said left is right, so I'm gonna start with left.
I think left.
Okay, I guess we'll start on the left. I heard two lefts and a right. Do two lefts make a right? No. Okay. Is it three lefts? No. All right, let's start with the left-hand side. Let's copy that down. Would changing to sines and cosines be something we could try? Why not?
It's already like that.
It's already like that. How about rewriting this fraction right here with a common denominator? Why not?
It's just one fraction.
It's just one fraction. Common denominator means you have two fractions with different denominators. I'm looking at the left-hand side. I don't have that. So the only trick I have left to try is the conjugate. And this one kind of screams conjugate at me because I see 1 minus sign. Look at what the conjugate is. What's the conjugate of 1 minus sign? Yep.
1 plus sign.
1 plus sign, and that's exactly what's in the other side. So that's probably a good direction to go because we're introducing something that ends up in the final answer. 1 plus sign, 1 plus sign. Now, here is kind of a very important rule. Anytime you have a problem and you have conjugates to multiply together, multiply the conjugates together first and don't do anything else. Okay, never do anything else. So I see two things I need to do. I have some stuff in the top and I have some stuff in the bottom. But the bottom is conjugates. Multiply those together. Don't do anything else in the problem. Keep the top exactly the same. And if you're thinking, well, isn't the top a distributive property? Should I distribute it? You're right, it is a distributive property. Don't do it. If you do it, it's going to end up worse. And you'll see why. So leave it just the way it is. Wouldn't it be great if this cosine just disappeared somehow? Because if it did, then I'd have exactly what I'm supposed to have in the top. So maybe it will disappear. Just leave it right there. Don't do anything with it. Let's FOIL the bottom out. What's 1 times 1? 1. What about 1 times sine? Sine and 1 times negative sine? So what's a positive sign and a negative sign? What does that give me? 0. Whenever you FOIL conjugates, the outer and the inner don't matter. They're always going to give you 0. So you do the first and you do the last. What's negative sign times positive sign? Negative sign squared. Look at the bottom. 1 minus sine squared. Let's go back here. What is 1 minus sine squared? Yep. Yeah. It's this identity rewritten. If you put the sine squared on the other side, 1 minus sine squared turns into cosine squared. So let's do that. Keep the top, 1 plus sine, and the bottom turns into cosine squared. Is there anything there that's common to the top and the bottom of that fraction? John? How many cosines on the top? How many on the bottom? How many are in common between the top and the bottom? One. One? One. I canceled out what was common to the top and what was common to the bottom. And look what you're left with. 1 plus sine over cosine. 1 plus sine over cosine. So anytime you see conjugates, distribute those first, and then hopefully it magically just cancels out something else in the problem that now you don't even need to think about. Okay. Questions on that? Which one do I want? That one. Still have a bunch of them to try. I'm not going to do all of them. I don't know. I guess.
Should we do the one with the triangle involved?
Which one? This one?
That one.
Okay. This will probably be the last one. So I'm not 100% sure what to do.
Won't that just be 1 over negative cosine x?
You can't cancel that. Like if you had this, let's just say, you can't say that that's negative 1/8.
Yeah.
Yeah, that doesn't, the 3 plus 2 doesn't cancel out like that. All right, so let's see what, I don't know, let's see what happens here. All right, I'll let you guys mess this up. So you tell me, what do you want to do first?
Change it to cosines.
Okay, yeah, I would try changing to sines and cosines, and I hope that something something cancels out somewhere. So what's secant?
1 over sine.
1 over cosine. So unfortunately, that one mistake could get you stuck for a half hour on this problem, because then nothing would work. You still might get stuck even if you do everything right, but just these problems are really kind of picky about little mistakes. So 1 over cosine. What's tangent?
Sin over cos.
Right, so sine over cosine. Okay, I like that common denominator already. That's a good thing that didn't have to happen, but it did. So I like that. What about in the bottom? Secant is what? 1 over cosine. Plus tangent, we just did. Sine over cosine. Minus cosine. Okay. But I kind of see where the top is going. So let's. I don't know. Let's just rewrite the top because I'm not 100% sure what we're going to do next here. But we already have a common denominator in the top. So let's just do 1 plus sine divided by cosine. So that I kind of saw. Any questions on that part? Okay, to the bottom, it looks kind of like a mess. So I'm trying to think what we want to do with that. First, let's make sure it's all correct. 1 over cosine, sine over cosine, minus cosine.
Would you change like the last one to cosine squared x over cosine? And then we can add that.
Well, you can put it over 1 if you want to make it a fraction. But you're saying make it a common denominator?
Yeah.
I think that's really the only option. I don't see. much else. Yes.
If you. Never mind.
Let's try the common denominator. I'm just not feeling good about that. I don't know why.
That'll work.
What's that?
I think it'll work.
Okay, let's try and see. So common denominator is going to be cosine. Oh, that's great because we have the same common denominator in the top part and the bottom part. So that's going to lead to canceling. That's good. Now we've got 1. That part already has the common denominator. Sine. That part already has the common denominator. What do I have to multiply top and bottom by here?
Cosine.
Cosine. So that's going to become a minus cosine squared over cosine. Okay, so we got that. Any questions on that? Now, does everybody see how these two things cancel out?
Yep.
Because if you were to flip and multiply, this cosine would go to the top and it would cancel this cosine in the bottom. So what you're left with now is this. 1 plus sine over, and remember this bottom one would be getting flipped and then multiplied. So this would end up in the bottom when you flip it and multiply. 1 plus sine x minus cosine squared. 1 plus sine x minus cosine squared. Okay. Now, I'm going to do one small thing here and see if you notice something. Very small step. I'm just going to change the order of those two. Make it 1 minus cosine squared plus sine. 1 minus cosine squared plus sine. Look at this. 1 minus cosine squared. Go back to this page.
Sine squared.
Yeah, I think I wrote that down. 1 minus cosine squared turns into sine squared. If we don't try that, I don't know what else we're going to try. I'm getting kind of stuck pretty soon if this doesn't help me. I don't know where I'm going to go from here. Ooh, perfect. So now I see everything that's going to happen. This is good. It's only good if I can find the problem. Okay, so we've got 1 plus sine over, what did we just say 1 minus cosine squared is? Sine squared plus sine. Now, look at the bottom. What do both terms in the bottom have in common? Sine. So what could you do if you had something like this? And I said to simplify it. Like what could you put on the outside here? Yeah, just x, and you could do something like this. Do exactly the same thing right there, and watch what happens. 1 plus sine. What can I factor out of the bottom? Sine. What would be left inside the parentheses if I factor sine out of this first one? Sine. And what would be left inside the parentheses if I factor sine out of here? Plus 1. Now, what do the top and the bottom both have in common?
1 plus sine.
They both have a 1 plus sine. That's like having like a 3 divided by 4 times 3. You have two things that are the same, so you can just cancel them out, and all you're left with in the top is a 1. Now we have 1 over sine. And what does 1 over sine turn into? Cosecant. I'm going to scroll back up, and I'm going to pray. That's what they said it should equal. Well, it was a simplify, so we don't know. I'm very confident that's what it should equal. I wish it said cosecant, but that's probably what it is.
This is an example from the book, or like all of the homework problems that I can do like that?
This one I would consider a medium to hard. This is a harder one. Most of them are going to be more like the other ones we did. Okay, but this is a good one to kind of show you what identities can turn into, and it can get really hard. I mean, like really hard. Like I can't even figure out what's going on, and I need help. But this one, I just kept trying the different tricks that we knew, change to sines and cosines, and as I did that, things just kept happening. Like something canceled out, right? Or then I found a common denominator, and then something else canceled out. The thing that gets frustrating in a problem like this is one little mistake and it blows up the whole thing. Then you're stuck. So sometime at that point, it's good to not even go back and try the same problem again. Go to a different problem because your brain might be stuck in that mistake. So you might do the same mistake again. Try a different problem and then maybe come back to this one that you're having trouble with later. Because if you're stuck in that mistake pattern, you're just going to keep repeating the same mistake probably. All right. But yeah, that was a tough one. That was number 10 on page 407. So I could check the answer, but I'm pretty sure that's right. All right, so homework, again, it's not a ton of questions, but remember some of them are going to take a little bit of time. So it's 4 through 8, 11, 12, 21 to 22, and 25 to 27.
So there's 10 problems.
Is that how many?
Yeah.
Yeah, so 10, 11, yeah. Okay, remember, I will be after school today, if anyone needs extra help. I will tell you that most of these problems they're more the easier ones. They're not all like the ones we did at the end. Might be one like that.
Are you free next period?